First, we will look at the relation between the densities of a liquid and an object floating in the liquid. So here is our object. Its volume is V. We will call its density rho O. Here is a liquid of uniform density rho L. Now let's suppose that 40% of this object is immersed in the liquid. This is 40% by volume now, not by mass. See, the density of this object might not be uniform. See, a lot of the mass could be concentrated in certain parts of the object. But we have to consider the volume that's immersed, not the amount of mass that's immersed. Okay, so let's assume that the volume that's immersed is 40% of the total volume V. 40% of V is 0.4 V. If the object has uniform density, well, in that case, 40%, the mass of the part that's immersed would be 40% of the total mass. But that's not necessarily the case. So I've just decided to make a note of what I said. If the object has uniform density, then the immersed mass is 0.4 times the total mass. So M is meant to be the total mass of this object. So for uniform density, the matter in this object is evenly spread out through this object. But anyway, it turns out that we don't need this object to have uniform density. We're only interested in the volume that's immersed, the fraction of the total volume that's immersed. This object is in equilibrium. Its acceleration is 0, so the resultant force on it by Newton's second law is 0. So its weight acts vertically down, as we know, and we have this other force acting up, the force on the object due to the liquid. It's called the buoyancy force. W is equal to B. We can apply the law of flotation to this object. The law of flotation, which comes from Archimedes' principle and the fact that the object is in equilibrium, says that W, the weight of the object, is equal to the weight of the liquid displaced by the object. So let's consider the weight of the object. Well, that's the mass of the object times G. Now what's the mass of the object? Well, it's the overall density of the object, rho 0, whether the density is uniform or not, times the volume of the object, V. And this is the mass. We multiply by G to get the weight. Now what about the weight of liquid displaced? Well, the volume of liquid displaced is equal to the volume of the immersed part of the object, which is 0.4 V. That's the volume of liquid displaced. And we multiply the volume by the density of the liquid displaced, rho L. This will give us the mass of the liquid displaced. So the mass of the liquid displaced times G gives us the weight of the liquid displaced. Notice that the relation between rho O and rho L doesn't depend on V, and the G's also cancel out. We see that rho O is 0.4 times rho L. So if 0.4 of a volume, or 40% of an object, is immersed by volume, then the density of the object is 40% the density of the liquid. Now, I could have chosen the immersed volume to be 50% of the total volume. In this case, the density of the object will be 0.5 times the density of the liquid. So it's a very simple relationship. So in general, this number is the fraction by volume of the immersed part of the object, or the percentage by volume of the immersed part of the object. In a previous video, we looked at how a spring balance works, and I just want to run through that explanation again. So here we have a mass whose weight is W. It's in equilibrium, so there must be an equal and opposite force acting upwards. If we call the mass M and the spring balance S, then we could call the force on the mass due to the spring balance FMS, force on M due to S. For equilibrium, this must equal W, the weight. But if there's a force on the mass due to the spring, there must be an equal but opposite force on the spring due to the mass. So this is just an application of Newton's third law. Well, actually I could put the tail of that vector at the point of contact of the spring with the mass. So this vector is the force on the spring due to the mass. But by Newton's third law, it's equal in magnitude to the force on the mass due to the spring, so it's equal to W in magnitude. So, as a reminder, here's the vector statement of Newton's third law. Now, the force on the spring due to the mass is the reading on the device. Now, let's consider this situation. The same object is immersed in a liquid. Its weight doesn't change, of course. Its weight is still W vertically down. Its weight is magnitude mg. There's a force on the mass due to the spring, which acts vertically up. Now, this is not the only force acting up on the mass. The mass is in contact with this liquid, so the liquid exerts an upward force on the mass, called the buoyancy force. Okay, so that's B. This force here is the force on the mass due to the spring. It's a contact force. Force on M due to S. Now this object is in equilibrium. Its acceleration is 0. We have the three forces acting on the mass. By Newton's second law, the resultant of those three forces is 0. So the forces pointing down must equal the forces pointing up. Now you'll often see the letter T used for this force, for string tension or spring tension or whatever. Now notice in this situation that the force on the mass due to the spring is less than what it is over here when the object is being weighed with no buoyancy force acting on it, when it's being weighed in a vacuum or even in air, because air exerts virtually no buoyancy force on an object. Again, to see the reading on the scale, we apply Newton's third law. Okay, we have a force on the mass due to the spring, so we must have an equal and opposite force on the spring due to the mass. The force on the spring due to the mass is the reading that we get here. But of course, FSM is equal to FMS by Newton's third law. So the reading in here is not W. It's going to be W minus B. It's going to be less than the reading when the object was weighed in air. It's going to be less by the amount B, the buoyancy force acting up on the object. The reading on the scale, that is the true weight of the object W minus the buoyancy force on the object, is called the apparent weight of the object. And we did an example of this in a previous video. Now let's consider this situation here. Here we have the container of liquid before the mass was immersed in it, and it's sitting on a scales. Now the scales gives us the weight of the liquid and the container actually. So I'd call that WL. Now the object is immersed in the liquid, so obviously the liquid level will rise. The scales. Well, we know that the liquid exerts a force on the mass in an upward direction, force of magnitude B. So by Newton's third law, the mass will exert an equal but opposite force on the liquid in the downward direction of magnitude B. So I'll put this arrow here to show that this is a force on the liquid. We can call it the force on the liquid due to the mass. We call the mass M. FLM. Well, that force on the liquid due to the mass is transmitted to the scales. We know that its magnitude is B. So the reading on the scales should increase by the amount B. So the new reading on the scales will be WL, the old reading before the object was immersed, plus B. So that's just an application of Newton's third law. The force on the mass due to the liquid is equal and opposite to the force on the liquid due to the mass. So we can read off the buoyancy force. We can read off what it is. We take the reading on this scale, on the scale after the immersion, and subtract the reading on the scale before the immersion. Now, by Archimedes' principle, we know that the buoyant force on an object is equal to the weight of the water displaced by the object. But what's the weight of the water displaced by the object? Well, it's the density of the liquid. Doesn't have to be water. It's the density of the liquid times the volume of the liquid displaced. But the volume of the liquid displaced is just the volume of the object. So mass of liquid displaced is density of liquid times volume of liquid displaced. And that volume is the same as the volume of the object. Multiply that by g to get the weight of the liquid displaced. So if we know the buoyancy force, which we can easily get by subtracting the readings before and after immersion, and let's suppose that we know the volume of the object. Okay, the volume of the object is easy to measure. We just look at the water level before and after the object is immersed in the liquid. So that'll give us the volume. The volume of water pushed up will equal the volume of the object. So we might know V and we might know B. Well, we can easily get rho L, the density of the liquid. We can just take the buoyancy force and divide by V times G.